Try sitting down with me and looking straight at a truth that almost no one stops to think about. We're told that the Big Bang was an explosion, a gigantic blast that started everything, a spectacular boom moment that kicked off the universe like holiday fireworks. But here's the problem. When you really look at the physics, when you examine the space, time models, when you calculate the energy, temperature, and how light behaves in a changing environment, when you compare the delicate data from the cosmic microwave background, you start touching an uncomfortable question. How could the Big Bang have been an explosion? If it exploded, where did it explode into? Into what? What space contained it? When space itself didn't even exist yet. And before you think I'm trying to create some artificial mystery, let me be clear. I believe in mathematics, in experiments, in nature, more than in any oversimplified story we tell each other. And that's exactly why this question grips me. Because when you do the math properly, when you let the physics speak for itself, instead of clinging to your intuition, the idea that the Big Bang was an explosion suddenly becomes not just wrong, but impossible. When people talk about the Big Bang, most picture a ball of matter exploding, flinging everything outward like a chemical or thermonuclear blast. But modern physics, from Einstein's field equations in 1915 to the observations of the 20th and 21st centuries, gives no support to that scenario. The Big Bang was not matter exploding. It was space itself expanding. This may sound strange, but it's the only thing that fits the data. Imagine you have an invisible grid stretched across the universe. Every point on that grid is a location in space. When the grid is stretched, the points don't run away, but the distance between them increases. Around 1929, when Edwin Hubble measured the recession velocity of galaxies by observing the red shift in their stellar spectra, he discovered something unmistakable. Every distant galaxy is moving away from us at a speed proportional to its distance. Following the relation, AR the new 500 kilometer /s/MPC at the time, the modern value is about 70 kilometers /s/MPC. That doesn't resemble any explosion that has ever existed. In an explosion, only the fragments closest to the center move the fastest. But here, the farther the galaxy, the faster it recedes. There is only one explanation. The space between the galaxies is expanding. The strongest evidence comes from light itself. When space expands, the wavelength of light gets stretched along with it, a phenomenon called cosmological redshift. No physical explosion can produce this uniform stretching on scales of billions of light years. Even the cosmic microwave background radiation, discovered in 1965 and possessing a temperature of only 2.725 K, shows a perfectly stretched spectrum exactly as predicted by the expanding space model. And most importantly, if the Big Bang were an explosion, it would have to have a center and an edge. But every observation from the 1960s to the present, from the 2DF survey to SDSS, confirms that the universe looks the same in every direction. No center, no edge, no point where the explosion began. Space does not expand into a larger space. It expands from within itself, everywhere, all at the same time. But here's the part that confuses people the most. If the early universe was as hot as about 10 Gindel K, and almost perfectly smooth, with fluctuations only on the order of 1 part in 100,000, then what caused it to grow into spiral galaxies, galaxy clusters, gigantic superstructures spanning hundreds of millions of light years? How does a universe as smooth as Saturn become such a complex architecture? If you want to find the earliest trace proving that the Big Bang could not have been an explosion in the usual sense, you have to look at the oldest thing we can observe, the cosmic microwave background, or CMB, the light released about 380,000 years after the Big Bang. and mapped in detail by the COBE satellite in 1992, followed by WMAP and Planck. All of these experiments repeat the same astonishing fact. The early universe was almost perfectly uniform, temperature variations of only about 1 part in 100,000. That is, think about it. Across patches of sky, billions of light years wide, the difference is so tiny, it's almost unbelievable. No explosion in nature can produce such a level of smoothness. Explosions always lead to chaos, random thick, thin patches, strong convective flows, uneven shock waves. But the CMB looks like an almost perfectly woven carpet, a subtle order hidden beneath the fiery surface of the early universe. And this is where physics begins to tell a very different story from popular imagination. Those tiny fluctuations on the CMB map are not just noise. They are acoustic oscillation modes, compression, rarefaction waves in the plasma of photons, electrons, and baryons, when the universe was still hotter than trillions of degrees. If you want a visual image, imagine tapping lightly on the head of a bongo drum. It doesn't vibrate randomly. It produces standing waves with fixed peaks and nodes, because the drumhead itself is a constrained physical system. The early universe was the same. When photons tried to escape the dense matter, but were pulled back by gravity, you got periodic oscillations, exactly like a gigantic musical instrument. This phenomenon is called baryon acoustic oscillations, or BAO. And here's the key point. An explosion never produces standing waves. An explosion only generates shock waves, turbulence, chaotic flows. It cannot produce a regular oscillation spectrum that we can still measure with extreme precision today. Yet Planck measured the peaks in the CMB power spectrum, called acoustic peaks, with accuracy to 1 part in 1,000. The first 3 peaks match perfectly with the predictions of the expanding plasma model. No explosion model has ever come close to producing anything like that. And it gets even more interesting. Each of those oscillation peaks corresponds to a beat of the universe, as the plasma rang like a bell. After the universe became transparent, during the recombination epoch, these ripples were frozen into the temperature map. You can think of them as the indentations left on a drumhead after you stop playing. Those tiny fluctuations, as small as 0.00001, are the seeds of the entire cosmic architecture. If the density was even slightly higher than average, just 0.001% higher, gravity would begin pulling matter together. As the universe continued to expand and cool, the denser regions gradually collapsed. After tens of millions of years, they became gigantic clouds of hydrogen and helium gas, larger than the future Milky Way. As the clouds collapsed, temperatures rose to millions of degrees, and the first stars, population 3, appeared roughly 200 to 300 million years after the Big Bang. These stars lived very briefly, but produced heavy elements, then exploded, seeding space with material for the next generation of stars. From that continuous activity, the first galaxies emerged. Soon after, galaxies merged to form larger systems, then galaxy clusters, and finally the cosmic web, a filament, void structure, stretching across hundreds of millions of light years, that surveys such as SDSS, BOSS, and DS have mapped. This is not random chaos. It is a soft fractal network with characteristic scales, with clear patterns of formation that trace directly back to the initial acoustic oscillation modes. Now go back to the original question. If the Big Bang were an explosion, what would you expect the universe to look like? You would see asymmetrically distributed debris, no regularity, no characteristic oscillation frequencies, no repetition across multiple scales. But the reality is the complete opposite. The universe looks as though someone set up an enormous resonator and let it ring with precisely defined modes from the very beginning. And there is only one mechanism that explains this. The universe did not explode. It expanded. And it expanded according to a specific mathematical law, governed by general relativity, plasma physics, and the interaction between photons and baryons. Those tiny fluctuations, seemingly insignificant, are what built everything: stars, galaxies, galaxy clusters, and the entire colossal structure of the universe. They are the clearest signature that the Big Bang was not a chaotic explosion, but an orderly expansion process, an unfolding of space in which minuscule ripples shaped the entire future of the cosmos. And to understand why those small oscillations could exist and grow, we have to go back even earlier, when the universe was not yet transparent, when light could not travel even a millimeter without being scattered back. This is the primordial plasma epoch, an extremely important phase that most human intuition is completely incapable of describing correctly. Imagine a pot of soup so hot that any bubble trying to rise is instantly crushed by the violent motion of the liquid. In the early universe, photons were those bubbles. They tried to move, but every few nanometers they were scattered by free electrons, redirected, pulled back, trapped in a dense plasma sea, at temperatures reaching tens of thousands of Kelvin, and earlier billions. This period lasted from about 1/1,000,000th of a second after the Big Bang until 380,000 years later, when recombination occurred. At a few minutes old, the temperature was around 10 far K. At 1 second old, the universe was still about 10 far K. This is an environment that no explosion on Earth, from thermonuclear bombs to artificial supernovae, can reproduce. And most importantly, no explosion can create such a uniform plasma environment. Plasma in an explosion is always chaotic, with huge density variations, turbulent flows, nonlinear shock waves spreading out. But the early universe was completely different. It was like a pot of soup stirred to near perfect uniformity. Electrons, protons, neutrons, photons, neutrinos, all distributed almost perfectly evenly across every region of space we can observe. This is not a sign of chaos. It is a sign of dynamical equilibrium in a rapidly expanding space where density and temperature decrease according to a simple yet extremely subtle law. Now imagine releasing a photon into this era. It cannot escape. Every few billionths of a second, it is knocked in another direction by an electron. In physics, we call this process Thomson scattering. And at that time, its efficiency was so high that photons were almost completely trapped in the plasma. Space at that moment was not an empty region through which matter flew. It was a dense, hot, thick medium in which light, the fastest thing in nature, became a prisoner. And here's the crucial point that the explosion model cannot handle. If the universe began with an explosion, it would produce extremely non-uniform plasma with clear directional development, a center of explosion, matter streaming outward. What we observe today is the exact opposite. No center, no preferred direction, no focused matter flows, no shock surfaces. The plasma is distributed with high precision and exhibits definite oscillation modes, meaning the universe was not blown apart, but oscillating within an expanding vessel. This can only happen if space is expanding at every point simultaneously, carrying the plasma along without generating any strong directional flows. It's like zooming in on a digital image. Every pixel expands at the same time. No pixel races ahead or gets distorted. The cosmic plasma behaved that way. The electrons and protons in the plasma epoch did not move away from an explosion center. Instead, the distance between them increased steadily with the expansion of space. The result is a stable, uniform, nearly flat environment in which the BAO oscillations we discussed earlier could develop harmoniously without being disrupted by chaos. This is also why the universe could preserve its acoustic signature. Until today, the plasma was not turbulent, as in an explosion, but constrained by photon pressure and gravity, oscillating like a gigantic drum as space expanded. Those oscillations produced the acoustic peaks that the Planck satellite measured with 0.1% precision. An explosion could not leave behind such a harmonic series of peaks over 13.8 billion years. And while the plasma existed, photons were completely locked in the sea of free electrons, unable to escape. The universe at that time was utterly opaque. If you had lived then, though that is impossible, you would have seen nothing but an endlessly scattered sea of white light. No stars, no galaxies, no sky, only a dense environment where light was trapped in perfect thermodynamic chaos. But it was precisely in that trapping that the universe prepared for one of its greatest turning points, recombination, the moment electrons and protons combined into neutral atoms, opening the door for photons to escape and creating the CMB we observe. The plasma is not evidence of an explosion. It is the characteristic stage of a uniformly expanding universe, where energy and density decrease according to precise laws. If the Big Bang had been an explosion, the plasma would have been chaotic, non-uniform, without harmonic oscillations, without a clear scattering boundary, and absolutely incapable of producing the smooth temperature picture that Planck has seen. And then, after hundreds of thousands of years of light being trapped in that dense plasma sea, the universe finally reached one of the most important phase transitions in its entire history, recombination. This is the moment when the temperature, after 380,000 years of expansion and cooling, dropped to about 3,000 K, low enough for electrons and protons, which had previously been continuously scattered by photons, to finally embrace each other and form neutral hydrogen atoms. This may sound simple, but it was the moment that completely transformed the face of the universe. Once electrons were no longer free, photons, the light that had been knocked around, redirected, and held captive for nearly 400,000 years, suddenly had no one left to block their path. No more free electrons to scatter them. No more foggy wall preventing light from escaping. For the first time in cosmic history, light could travel straight and free. And the very light released at that moment, the moment physics calls photon decoupling, is exactly what we measure today as the cosmic microwave background, with an average temperature of 2.725 K. That ancient light has traveled 13.8 billion years to reach our eyes. When you look at a CMB map created by the Planck satellite, you are actually looking at the last surface where light was ever trapped. It's like the moment you open the bathroom door. After a hot shower, the steam rises, then slowly dissipates, and you see the room clearly again. Recombination was that moment when the steam disappeared on a cosmic scale. And this is where every Big Bang as explosion model completely collapses. If the Big Bang were an explosion, you would expect the light released in an explosion to be non-uniform. Any explosion creates enormous temperature gradients, shock waves, shock fronts, uneven dense, rarefied matter flows, and extremely strong asymmetries. Look at photographs of a thermonuclear bomb explosion, or even a supernova. No part is perfectly symmetric, but the CMB, the light released at recombination, has absolute uniformity at the 99.99% level, with only the tiny nth ninth of fluctuations you saw earlier. You cannot emphasize this enough. No explosion in nature can produce such a uniform radiation field on scales of billions of light years. Imagine throwing a bomb into a lake. The water surges, waves spread, but every region oscillates completely differently. Now imagine that lake is as wide as the observable universe, and you claim this explosion produced waves as even as a sheet of glass. That would be absurd. Yet the CMB is uniform, to the point that even a 0.01% deviation would make our cosmological model incompatible with Planck data. This uniformity can have only one cause. The universe at that time was not exploding, but expanding uniformly, causing the temperature to decrease evenly across space and time, creating a velvet-smooth curtain of light. When recombination occurred, the emitting surface, called the last scattering surface, was not the surface of an exploding sphere, but the entire three-dimensional space, reaching the condition for neutral hydrogen to form at the same instant, everywhere, in every direction, wherever you look. And this explains another mystery that makes the explosion model even more nonsensical. Why every point on the sky has nearly the same temperature, even though they are separated by tens of billions of light years, and could not have exchanged information at the speed of light in the short time after the Big Bang. This is called the horizon problem, and it is one of the reasons scientists had to abandon the explosion idea and move to the expanding universe model, a model later even more powerfully reinforced by the hypothesis of inflation. But even before inflation, recombination alone is enough to thoroughly undermine every explosion picture in cosmology. The light we see today, CMB, is the remnant of the most uniform light release moment in history, not a frantic flash from an astronomical explosion. And when scientists in 2003 examined the WMAP data, they saw that what Bell Labs discovered in 1965 was only the tip of an astonishing truth. The sky is covered by a temperature carpet, so uniform that no explosion could have caused it. This release of light is a clear, powerful, and undeniable signature that the universe was not created by an explosion. It is the imprint of an expanding space-time field in which every physical condition changed uniformly. When recombination occurred, the entire universe transitioned from opaque to transparent in a single turning point, leaving us with a frozen photograph of that very moment. When the light finally escaped from the plasma, leaving behind the transparent universe for the first time in history, we could peer deeper into the subtle but extraordinarily important ripples that etched the structure of the universe like ancient musical notes. Those ripples are called baryon acoustic oscillations, abbreviated as BAO. And if you want to understand why the Big Bang could not have been an explosion, BAO is one of the pieces of evidence that nature has recorded so clearly it is impossible to deny. Let's start with a very easy to understand picture. Imagine in front of you is a bongo drum. When you tap on the drum head, the sound doesn't just spread out. The entire drum head vibrates in specific patterns, standing waves, with peaks and nodes appearing at fixed positions. You can change the force of your tap, but the overall shape of the oscillation modes still obeys the laws of the drumhead itself. How tight it is, its shape, what material it's made of. Now, scale that image up to the size of the early universe. Instead of a drumhead, you have a hot plasma sea of photons, electrons and baryons. Instead of your finger tapping the drum, you have gravity from slightly denser regions, pulling matter in. And instead of sound, you have radiation pressure, the pressure of photons pushing against baryons, pushing matter out. These two forces continuously pull and push, just like tapping steadily on a drum. The result, the universe rings with acoustic patterns like a gigantic musical instrument. That is BAO. To understand why this matters, recall a point from earlier. The oscillations in the CMB have an amplitude of only about n. That means the dense rarefied regions in the plasma did not become chaotic or break apart. Instead, they oscillated rhythmically, like gentle water waves in a very still lake. The universe at that time, roughly from 10,000 years to 380,000 years after the Big Bang, was not like a chaotic explosion, but like a resonant chamber where baryon acoustic waves traveled back and forth according to clear rules. And this is where the explosion model fails completely. An explosion produces shock waves, turbulence, chaotic flows, no stable oscillation modes, no periodic sound, lasting hundreds of thousands of years. An explosion is the breaking of structure, not the building of structure. But BAO is building. When you let plasma oscillate in a slowly and uniformly expanding environment, acoustic waves develop at specific frequencies, acoustic modes that we see very clearly today in the CMB power spectrum, the acoustic peaks. It is precisely these peaks recognized by the 2006 Nobel Prize, awarded to the Koch team, and later measured by Planck with astonishing precision, that confirmed BAO is real. But BAO does not only exist in the CMB. They left traces in the distribution of galaxies billions of years later. Here is the amazing part. Each ancient acoustic ripple propagated outward in the plasma at about 150,000 km, half the speed of light, for 380,000 years. When recombination occurred, the sound waves stopped, but the position of the last wavefront remained imprinted in the matter density. That means, for each initial oscillation center, there is a ring of matter at a radius of about 150 mpc, equivalent to 500 million light years. That is an enormous number, but so precise that galaxy surveys, such as SDSS, BOSS, and DISE, all observe a preferred distance peak in the separation between galaxies, exactly at that scale. This is not coincidence. This is the signature of BAO, ancient sound waves, frozen into the structure of the universe. If the Big Bang were an explosion, you would never see concentric expanding ripples of the same size, repeating on scales of hundreds of millions of light years. An explosion does not create a standard ruler, but BAO does. That is why BAO is now used as one of the standard rulers to measure the expansion of the universe, competing with Type Ia supernova, and even helping clarify the Hubble tension. What does the existence of BAO tell us about the nature of the Big Bang? That the universe did not explode like a bomb. Explosion chaos. Chaotic plasma cannot produce periodic acoustic waves. It cannot maintain harmonic modes for 380,000 years. It cannot create a standard radius. But our universe has all of those things. So what created BAO? The combination of steady, uniform expansion of space, strong plasma interactions, and stable gravitational force. As space expanded, plasma stretched along with it, preserving the oscillation modes from disruption. When photons pushed baryons outward and gravity pulled baryons inward, we got drum-like oscillations. When recombination ended the interaction between photons and baryons, the sound waves stopped, leaving a permanent imprint. One could say BAO is the final echo of the early universe. The most fascinating thing is that BAO not only explains why there are preferred rings in galaxy distribution, it also explains why the large-scale structure of the universe has a soft fractal character with characteristic scales rather than randomness. It explains why galaxies, galaxy clusters, superclusters, and gigantic voids are not products of chaos, but the result of a structured oscillation process. This is something only the expanding universe model, not an explosion, can produce. So when you look at BAO, you are looking at living proof that the universe did not form from a chaotic explosion. You are looking at the primordial rhythm, the first music of the universe, a symphony composed by plasma, gravity, and expanding space. And every time we measure BAO more precisely, we are listening more clearly to the echo from the time when the universe had no stars, no galaxies, nothing except gentle ripples in a hot plasma sea. Those echoes tell us a story that an explosion could never tell. The universe did not explode. It rang, and it rang according to a law so beautiful, it is almost surreal. If plasma and BAO are the music of the early universe, then dark matter is the stage builder, a silent character that does not emit light, does not interact electromagnetically, does not reflect light, yet constructs the entire framework onto which baryons, gas stars, and galaxies will settle like cosmic cement. I often joke that dark matter is the character the universe hired to build the structure, but never allowed to appear on stage. It doesn't speak, doesn't create lighting effects, doesn't tell stories, but if you remove it from the universe, everything else collapses immediately. To understand why, we need to look at what happens after recombination. When photons stopped scattering baryons, ordinary matter, hydrogen, helium, a little lithium, could finally hear the call of gravity. But here is the problem. Baryons alone cannot form galaxies in the time we observe. They are too hot, too thermally active, and it takes far too long for small overdensity regions to grow into large structures. If the universe had only baryons, the first galaxies would not form 300 million years after the Big Bang, as we see. But billions of years later, far too late compared to data from JWST or Hubble. So baryons needed something to pull them in, something extremely cold, extremely massive, and completely unaffected by photon pressure. That is dark matter. It created gravitational wells, invisible gravity pits, very early, even before the universe had cooled much. When recombination occurred, baryons fell into these wells like rain falling into valleys. Explosion? It cannot create this. An explosion cannot build a skeleton. It only throws debris outward, distributed randomly in chaotic directions. But dark matter is not random. It follows exactly the small fluctuations we see in the CMB. It does not depend on light. It does not feel radiation pressure. And that is why it began to clump first, forming the framework before baryons could do anything. When the universe was only a few tens of thousands of years old, dark matter had already started forming halos, invisible masses that would later become the centers of galaxies. Baryons were pushed outward by photons and had to wait for recombination to fall in. This explains why dark matter must account for about 27% of the energy, mass content of the universe, while baryons make up only about 5%. If that ratio was slightly different, galaxies would not form on time, or not form at all. Imagine a universe with only baryons and no dark matter. Every small overdensity would be disrupted by radiation pressure and thermal motion. Without a frame for baryons to cling to, the universe would remain a diffuse hot gas fog that never condenses into stars. Even the smallest galaxy could never form. And without galaxies, no stars. Without stars, no carbon, oxygen, nitrogen, and without those elements, no you and me. But dark matter does not only explain galaxy formation, it also explains their strange rotation speeds. In the 1970s, Vera Rubin observed rotation curves of spiral galaxies and found that stars were orbiting far too fast for the amount of visible matter. If there were only baryons, galaxies would be torn apart. Yet in reality, they remain intact. The reason? A gigantic dark matter halo surrounding them, providing the gravitational force to hold everything together. An explosion cannot explain this. An explosion cannot create stable, uniform, millions of light years wide structures like dark matter halos. It cannot wrap galaxies in a symmetric, spherical, invisible gravitational mass. Explosion chaos, asymmetry, no regularity, dark matter symmetric, dense framework, formed according to the initial oscillations. The terrifying precision lies in the fact that dark matter exactly mirrors the fluctuations measured by the CMB. Slightly denser regions in the CMB became the places where dark matter clumped first and baryons followed. Slightly rarer regions became voids hundreds of millions of light years wide. Dark matter is the architect of the cosmic web, while baryons merely paint color onto the drawing it created. When you look at the largest galaxy distribution maps today, from SDSS to DSE, you do not see the chaos an explosion would produce. You see a structured network with filaments stretching hundreds of millions of light years and gigantic voids. All of it originates from where dark matter concentrated from the very beginning. If you remove dark matter from the equation, galaxies do not form. Galaxy clusters do not exist. The cosmic web disappears, and the universe becomes a shapeless fog. But dark matter did not arise from an explosion. It arose from an orderly expansion process, where gravity and plasma physics interacted over hundreds of thousands of years to create fluctuations we still measure today. Therefore, when we say dark matter is the invisible skeleton of the universe, it is not just a metaphor. It is an observed physical reality. It is the foundation for all large-scale structure. And once dark matter has finished its role as stage builder, the universe enters the phase in which everything we see in the night sky, every galaxy, every star, every planet, every carbon atom in your body, originates from a wondrous but strictly law-abiding sequence of physical processes. Galaxy formation. It all began when baryons, the hydrogen, and helium gas left over from the Big Bang fell into the gravitational wells that dark matter had formed very early, around 30,000 to 100,000 years after the Big Bang, when radiation energy had decreased enough for dark matter to dominate large-scale structure. The overdense regions in dark matter, which we see reflected in the Ten-Harkless fluctuations of the CMB, began pulling baryons in, creating gigantic gas clouds with masses from 10 Hark to 10 Harp solar masses. As the gas was compressed, temperature rose to millions of Kelvin, and at a critical point, protons began fusing, releasing energy. The first stars ignited. These population 3 stars formed roughly 300 million years after the Big Bang, according to 2023 JWST data, observing extremely early galaxies such as Glass Z, 12 Orseus 1749. They were gigantic stars, possibly 100-300 times the mass of the Sun, lived very briefly, only a few million years, then exploded in extremely energetic supernova, producing carbon, oxygen, silicon, iron, the first heavy elements in the universe. But the important point is, all of this took place in a gravitationally ordered space, not in chaotic debris from an explosion. Think about the collapse process. As the gas cloud contracted, it began spinning faster to conserve angular momentum, just like a figure skater spins faster by pulling their arms in. From this rotation, galaxies began to take on disk shapes. Modern simulations, such as Illustrist NG, show that a dark matter halo of 1,000 solar masses, comparable to the future Milky Way, will produce a stable rotating disk within just a few billion years. This is something an explosion could never create. An explosion produces debris flying off in all directions, with no regularity, no preferred rotation axis. But galaxies require a stable amount of angular momentum, conserved and amplified over hundreds of millions of years. Spiral galaxies, like the Milky Way or Andromeda, show this clearly. They have symmetric spiral arms, rotating at about 220 kilometers per s at the Sun's position. 26,000 light years from the galactic center. If this were the product of debris from an explosion, everything would fly straight outward, and the galaxy would disintegrate after just a few rotations. Yet galaxies endure for billions of years. We know this thanks to rotation curve observations by Vera Rubin in the 1970s. The flat rotation curves of galaxies are undeniable evidence that dark matter is holding the structure together, creating a stable gravitational frame that an explosion could never recreate. Now look at what happens after the first stars ignite. When massive stars explode, a supernova releases hundredth volts of energy. The shock waves spread out, compressing nearby gas clouds. This triggers new star formation, but at the same time, supernovae also release enough energy to blow some gas out of the galaxy center, slowing down the star formation rate. This is feedback, and feedback is why galaxies do not collapse completely into themselves. When feedback is weak, galaxies form stars too quickly, depleting the gas cloud in just a few 100 million years, like the starburst galaxies Hubble observed, such as M82. When feedback is strong, gas is pushed far away, star formation slows, and the galaxy maintains balance for billions of years. None of this process resembles debris after an explosion. Debris does not self-regulate. Debris does not recycle. Debris does not have a star formation feedback regulation loop. Debris simply flies away, disperses, loses energy, and stops interacting. But galaxies are different. Galaxies have life cycles. Galaxies have directed evolutionary histories. Galaxies have patterns, order, rhythm. And this is clearly demonstrated in the largest galaxy distribution observations we have ever made, from SDSS, BORS, to DS. When we look at maps of millions of galaxies, we see nothing resembling an explosion. Instead, we see filaments, voids, nodes, a gigantic three-dimensional network with extremely clear statistical laws. Filaments stretch up to 300 million light years. Voids span 100, 200 million light years. Galaxy clusters like Virgo or Coma contain thousands of galaxies bound by dark matter gravitational fields. No explosive mechanism can create this. Explosions do not create filaments. Explosions do not create symmetric voids. Explosions do not create the soft fractal distribution we observe. Only gravity acting on small initial perturbations in an expanding space can produce such ordered structures. To make it clearer, imagine the universe as a stage being gradually constructed. Dark matter builds the skeleton first, then baryons pour onto the frame. Gravity pulls in, radiation pushes out, feedback sets the rhythm. Supernova recycle material, gas cools, new stars form. Spiral arms are maintained by density differences. Galaxies merge, collide, rotate, and settle into new shapes. It is a directed process lasting billions of years, and most importantly, it fits observational data perfectly. Meanwhile, if the Big Bang were an explosion, you would expect a universe with random lawless distribution, no acoustic peaks, no BAO, no filaments, no stable rotation curves, no dark matter halos, no preferred rotation axis. But we see all of those things. They do not merely exist. They match the expanding universe model to an astonishing degree. Therefore, when you look at a galaxy, any galaxy, from dwarf galaxies with just a few 100 million stars to monster galaxies like IC 1101 with 100 trillion stars, you are looking at clear evidence that the Big Bang was not an explosion. No chaotic debris could ever self-organize into perfect spiral arms, into stable dark matter halo rings, into regulated star formation cycles controlled by feedback, into a structured cosmic web spanning hundreds of millions of light years. The only way galaxies can exist is if the universe began with orderly expansion, where the small perturbations of the early universe were gradually amplified by gravity over time. When you look up at the night sky, every galaxy is a reminder the universe did not explode, it grew. It is not chaotic, it is organized. It did not fling matter outward, it built structure. And that is why galaxy formation, with all its patterns, data, and structure, completely refutes the idea that the Big Bang was an explosion. And when the first galaxies appeared and gradually grew over time, you begin to see an even more majestic picture. The entire universe is not distributed randomly at all, but instead has a structure so vast that it exceeds all our previous intuitions. If you zoom out from a single galaxy to a galaxy cluster, then to a supercluster, and keep zooming out, you will not see a meaningless chaotic cloud. You will see something that looks strangely familiar, a gigantic spiderweb network stretching across hundreds of millions of light years, with thin but long filaments connecting dense nodes where galaxy clusters concentrate, and interspersed between them are immense voids, voids hundreds of millions of light years wide, where almost nothing exists. This is the cosmic web, the largest architecture in the universe, and also one of the most convincing pieces of evidence that the Big Bang could not have been an explosion, because an explosion does not create a web. An explosion does not create scale invariance. An explosion does not create regular filaments, concentrated nodes, and spacious voids. An explosion only creates chaos. But the cosmic web is not chaotic. It has structure. It has geometry. It has hierarchical scales that we describe with power law distribution functions, a hallmark of self-similarity. This is not what you would expect from debris shot out from an explosion center. This is what you expect from small density fluctuations being amplified in an expanding space under the quiet guidance of dark matter. Imagine you have a piece of sea foam with a network of interconnected small holes. Now think of a version of that foam scaled up billions of times, where each strand is as long as dozens of galaxy clusters, and each hole is hundreds of millions of light years wide. That is exactly the cosmic web. And what makes it remarkable is we see this pattern at every sufficiently large scale. When astronomers map millions of galaxies, they find that the universe has filaments about 100–300 million light years long, flat sheets that stretch out, and empty voids occupying roughly 60% of the universe's volume. This is not a random Poisson distribution. It is a structure with extremely clear statistical patterns. So what creates this web? It is dark matter plus the expansion of space. Dark matter, with its role as the silent stage builder, concentrates first in the filaments, forming the skeleton of the web. Baryons fall into these filaments, creating stars, galaxies, galaxy clusters. Meanwhile, low-density regions are depleted of matter by dark matter, leaving behind gigantic empty voids. One important point: this web has no center, no preferred direction of explosion, no sign whatsoever that matter was blown outward. Every part of the web looks like any other part, as long as you look on a large enough scale. This is precisely the homogeneity and isotropy that the standard cosmological model relies on. An explosion cannot create global isotropy. A bomb does not produce a hierarchical network with statistical repetition. It produces fragments, shock fronts, and strong directional asymmetry. But the cosmic web matches extremely precisely what happens when small perturbations, 10⁄2 a year, are gravitationally amplified in an expanding space. Consider the process from a physical perspective. In slightly overdense regions, gravity pulls matter in faster, causing dark matter and baryons to flow toward them. In slightly underdense regions, matter lags behind, creating voids. As space expands, overdense regions do not expand as quickly as their surroundings, allowing them to gravitationally dominate and become large nodes. Other regions become filaments connecting these nodes. Over billions of years, this natural pull-squeeze pattern produces the web shape we observe. The filaments, hundreds of millions of light years long, are not accidental. They are the result of the growth rate of initial fluctuations under the influence of dark matter. The gigantic voids, 100, 200 million light years wide, are not regions missed by an explosion. They are places where the initial overdensity was too small for dark matter to concentrate. Even enormous superclusters like Laniakea, the supercluster that contains the Milky Way, are merely large nodes in this network. When scientists run n-body simulations with billions of dark matter particles, they always obtain the same result, a cosmic web identical to the real universe. But if you run an explosion simulation, debris shot outward from a blast, you will never get filaments, no scale invariance, no long-range correlation distribution, no symmetric voids, no gigantic nodes. All you get is an expanding, thinning cloud of matter. No structure, no hierarchy, no map. The real universe is the opposite. The universe looks as though someone wove a gigantic lattice out of dark matter, then draped baryons over it. When you look at a 3D map of millions of galaxies, you cannot help but see that the cosmic web is almost a mathematical work of art, beautiful, intricate, and consistent to an almost unbelievable degree. No explosion could do that. Only the expansion of space plus gravity, plus dark matter, plus initial small perturbations can produce the cosmic network with the shape we observe today. In other words, the cosmic web is not just a large structure. It is a statement. It says that the Big Bang was not an explosion. It says that the universe was not blown apart. It was woven. It grew as a directed structure, not as disorganized debris. And when you have seen the cosmic web stretching out like a gigantic cosmic lattice, you might think we only understood this thanks to modern satellites, supercomputers, and large-scale galaxy surveys. But in reality, the first piece that put an end to the explosion idea appeared nearly a century ago, between 1923, 1929, when a man standing on a mountaintop in California began observing faint patches of light that people at the time thought were merely nebulae inside the Milky Way. That man was Edwin Hubble, and he did something that completely changed humanity's understanding. He proved that the Milky Way is not the entire universe. When Hubble observed Cepheid variables in the Andromeda Nebula, he measured a distance of 2.5 million light years, far beyond the size of the Milky Way. That meant Andromeda was a separate galaxy, not a gas cloud inside the Milky Way. The universe suddenly became vastly larger than anyone had imagined. But this discovery was only the opening step. What made Hubble an icon of astronomy was not just discovering galaxies beyond the Milky Way, but the relationship between distance and redshift, the relationship we now call Hubble's law. When Hubble and Milton Humason analyzed the spectra of dozens of distant galaxies, they noticed that the light from those galaxies was shifted toward the red, a sign that they were moving away from us. And not just that, the farther the galaxy, the greater the recession speed. This linear relationship was published in 1929, and it is one of the most important scientific discoveries in history. Pause for a moment to understand why this shatters the explosion picture. Because if the Big Bang were an explosion in space, what would you expect? You would expect fragments flying out from a central point. Fragments near the center would move fastest. Fragments farther out might slow down, depending on initial energy. You would expect a chaotic, asymmetric distribution. You would expect an expanding bubble of debris within a pre-existing space. But that is not what Hubble observed. Instead, he saw that every distant galaxy is receding from us, and more importantly, a galaxy in one direction recedes from us at the same rate as a galaxy in the opposite direction. No preferred direction, no center, no edge, no shock front. This can only happen if space itself is expanding, not if matter is exploding outward into space. Imagine a balloon being inflated. 2 points on the surface that are farther apart get pulled apart faster. Every point feels as though everything is moving away from me. This is exactly what the universe is doing, and it is exactly what an explosion cannot do. In an explosion, space does not stretch. Matter is simply thrown outward into existing space. In the universe, matter is not racing through space. Space is stretching and carrying matter along with it. This is the fundamental difference that human intuition, built from throwing rocks, watching fireworks, and seeing steam rise, is not subtle enough to grasp. But the data see it very clearly. Even though Hubble's initial Hay value was wrong, he gave about 500 Kelman/S/MPC, while the modern value is around 70 Kelman/S/MPC. That does not change the truth. Recession velocity is proportional to distance. An explosion does not produce such a simple, elegant, linear relationship. Only the expansion of space can. And here, I must emphasize something that many people, even very smart ones, sometimes forget. Data do not care about your intuition. Your intuition may say the Big Bang must look like an explosion, but the sky disagrees. Your intuition may say distant galaxies recede at high speed because they are running away from us, but the spectra disagree. Your intuition may say the universe must have a center, but every observation from SDSS to DF, DSI to Planck disagrees. When you look at what Hubble measured, those red-shifted spectra, like long red streaks across time, distances so vast they are hard to believe, and that surprisingly beautiful linear relationship. You are looking at the first piece of evidence in history against the explosion idea. And if Hubble's discovery was the first blow against the explosion picture, then the second blow, and perhaps the most fatal one, came in 1964, when two Bell Labs radio engineers, Arno Penzias and Robert Wilson, accidentally heard what humanity had missed for decades. The lingering echo from the early universe, the ancient light released during recombination that we discussed earlier, the cosmic microwave background, CMB. The story began when Penzias and Wilson were using a horn-shaped antenna, the Holmdel horn antenna, to test satellite signals. But no matter where they pointed the antenna, no matter day or night, no matter how carefully they checked the equipment, a strange noise was always there, a uniform hiss coming from every direction in the sky, equivalent to blackbody radiation at about 3 Kelvin. They thought it was a technical fault. They eliminated electrical interference. They fixed the receiver. They even cleaned pigeon droppings out of the antenna because they thought the birds were causing the noise. But the noise remained, and the strangest thing, it was completely uniform, not stronger in one direction, not weaker in another. It blanketed the sky like a perfectly even temperature blanket that no explosion in nature could produce. Finally, when they contacted the theoretical group at Princeton University, including Robert Dick, Jim Peebles, Peter Roll, and David Wilkinson, they realized the crazy thing they had accidentally discovered. They were hearing the cosmic microwave background radiation, light that had traveled 13.8 billion years to reach Earth. The CMB immediately became the strongest evidence that the universe did not begin with an explosion in the familiar sense, because if it were an explosion, you would expect extreme chaos, asymmetrically distributed hot-cold regions, shock waves varying dense rarefied structures in every direction. But the CMB is almost perfectly isotropic, with an average temperature of 2.725 K and fluctuations of only about 0.0003 K after cold. Measured it in 1992. An explosion does not produce this. An explosion cannot produce a radiation field uniform to 1 part in 100,000. Every explosion you have ever seen, from fireworks to chemical bombs to supernovae, has asymmetric temperature structure, hot regions, cold regions, compressed regions, rarefied regions, all random. But the CMB is not random. The CMB is an unbelievably smooth temperature map, and most importantly, it comes equally from every direction. If the Big Bang were an explosion, you would see clear temperature differences between the direction opposite the explosion center and the direction along it. But the CMB has no preferred angle. It has no explosion direction. It has no edge. It has no wave crest, only near perfect isotropy. This fits perfectly with the expanding universe model, but completely contradicts the explosion model. The CMB is like a childhood photograph of the universe, and that photograph says that at 380,000 years old, the universe was expanding uniformly, not being blown outward. Even the tiny fluctuations that Kolbe, WMAP, and Planck measured, those small blue, red spots on the CMB map, are not traces of chaos. They have harmonic structure, clear frequencies, oscillation peaks precisely described by acoustic plasma theory. Those fluctuations are the legacy of the BAO we discussed in part 6. An explosion does not produce harmonic modes. An explosion does not produce acoustic peaks. An explosion cannot leave behind traces that persist over billions of light years with such astonishing precision. The CMB, very straightforwardly, is the universe's birth certificate, and that birth certificate does not say the universe exploded. It says the universe expanded, cooled, underwent phase transition, became transparent, and left behind ancient light as a reminder that every point in the universe was once much more tightly connected than it is now. When Penzias and Wilson's report was published in 1965 in the Astrophysical Journal, they could not have imagined that their annoying noise would become the single most important foundation of modern cosmology. It is evidence so strong that the explosion model cannot stand for even a second against it, because 99.99% isotropy is the signature of uniform expansion, not of an explosion. The discovery of the CMB paved the way for the most precise series of cosmological experiments in human history, and each one drove another nail into the coffin of the Big Bang as explosion idea. Kolbe, WMAP, and Planck did not just measure background radiation. They measured how the universe breathes, how it oscillates, how it expanded from the earliest times. The data are so refined that if the explosion model had even a sliver of hope left, these 3 astronomical missions extinguished it completely. It began with Kolbe, launched in 1989. Kolbe was designed to check whether the CMB really is blackbody radiation. Before that, many still hoped the CMB might be light from distant stars, hot dust, or some mixed radiation. But when Kolbe released its results in 1992, the CMB spectrum appeared so beautifully that no one could believe it. A perfect blackbody curve at 2.725 K, matching Big Bang theory to 1 part in 100,000. No explosion in nature produces such a perfect blackbody spectrum. Explosions always produce messy, non-uniform spectra with many random components. But the CMB is as smooth as an ideal curve from a physics textbook. This is strong evidence that the universe was once in a state of pure thermal equilibrium, a state that can only exist in a uniformly compressed and uniformly expanding plasma, not in chaotic explosion debris. In addition to measuring the spectrum, Kolbe detected anisotropy at the level of 100 C, small temperature fluctuations that we later learned are the seeds of the entire cosmic structure. An explosion cannot produce these regular small fluctuations, but an expanding universe can. Kobe's achievement was so great that its science team received the Nobel Prize in Physics in 2006, but that was only the beginning. Next came WMAP, launched in 2001. If Kobe gave us a blurry picture of the CMB, WMAP gave us HD resolution. WMAP's resolution was 30 times better than Kobe's, enough to measure fine details of hot-cold regions in the CMB, enough to determine the shape of the universe, spatial curvature, dark matter density, baryon density, and even the age of the universe, 13.7, 3.0.1, 2 billion years, 2003 result. WMAP also measured the first 3 acoustic peaks in the CMB power spectrum, clearly for the first time. Those peaks come from the ancient BAO sound waves we discussed, and their appearance, precise in position and amplitude, is something an explosion could never produce. An explosion has no mechanism to create periodic oscillatory modes in plasma, but an expanding universe plus photon, baryon coupling does. WMAP data revealed an important truth. The universe does not just expand, it expands with extremely delicate initial conditions, exactly as predicted by the inflation model. If the explosion model ever had any chance of being correct, WMAP took away every last chance. But if you want to see what truly annihilated the universe as explosion idea, you must look at the third mission, Planck, the ESA satellite launched in 2009, collecting data until 2013. If Kobe was a blurry photo, WMAP was a sharp photo, then Planck is a 4K ultra-sharp image of the early universe. Planck measured the CMB temperature with precision to hentosopix and created the most detailed anisotropy map ever made. Planck's results left the entire scientific community speechless. The CMB spectrum matches the current standard lambda CDM model at the 0.1% level, nearly perfect. Acoustic peaks extend to the 7th, 8th peak and still match theory. The distribution of fluctuations is nearly perfectly Gaussian. No clear signs of shock waves, asymmetry, or anything an explosion would leave behind. But the strongest thing Planck brought was indirect evidence for inflation. A super rapid expansion phase, right after the Big Bang. Inflation explains why the CMB is nearly uniform, why the universe is flat, why causally disconnected regions have the same temperature, why CMB fluctuations are nearly Gaussian, why there are periodic acoustic peaks. An explosion explains none of these. An explosion does not flatten space. An explosion does not remove defects. An explosion does not create Gaussian fluctuations. An explosion certainly does not produce a perfect Planckian spectrum. This is not just failure. This is physical impossibility. Most importantly, Planck confirmed that the cosmic background spectrum is the most perfect black body ever measured in nature, smoother than any black body spectrum we create in laboratories. An explosion cannot produce a silk-smooth spectrum like that. It is the trace of a dense, uniformly expanding plasma, not of debris shot into space. When you look at these 3 experiments, Kobe, WMAP, Planck, you see the same story told in 3 different voices, but with identical content. The Big Bang was not an explosion. Kobe says, this is a perfect black body spectrum. An explosion cannot produce this. WMAP says, these are ancient harmonic oscillations. An explosion cannot leave such a pattern. Planck says, this is detailed data, point by point across the sky. The universe follows inflation, not any explosive model. And the truth is, there is no longer any corner for the universe began with an explosion idea to hide in. No more room for that misleading metaphor. No more reason to cling to intuition when the data have spoken so clearly. The CMB is the young universe's last will and testament, and the 3 missions Kobe, WMAP, Planck have read that will word by word, detail by detail, oscillation by oscillation. The content of the will has not changed. The universe did not explode. The universe expanded. The universe oscillated. The universe obeyed the mathematics of curved space and hot plasma, not the logic of bombs and fragments. This is the moment when the idea, Big Bang equals sign explosion, is not just wrong. It is dead, nailed shut in its coffin by pure data. When observations from Kobe, WMAP, and Planck had nearly extinguished every remnant of the explosion model, the universe still had one more shock in store for us. One that not only completely demolished the idea of an explosion, but also forced all of modern physics to reconsider how it understands space and energy. That shock arrived in 1998 when two independent research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Ries, announced something no one expected. The universe is not only expanding, it is expanding at an accelerating rate. They measured distances to Type Ia supernovae, those extremely stable standard candles, and compared the observed brightness with the predicted brightness. When the data were analyzed, the result was earth-shaking. More distant galaxies appeared fainter than expected in a constant expansion model. That could only mean one thing. The universe is expanding faster over time. No one anticipated this. No theory had predicted it beforehand, but it happened. And the name we gave to the cause is dark energy, a mysterious component that accounts for about 68% of the total energy of the universe, according to the 2018 Planck data. Now think about what this means for the Big Bang as explosion model. In an explosion, fragments are ejected with an initial velocity. Then they slow down, no exceptions. Gravity, drag, or simply energy dissipation all cause debris to decelerate over time. No bomb explodes and then, billions of years later, its fragments suddenly speed up again. That is completely contrary to every law of dynamics we know. But the universe does exactly the opposite. It expanded slowly in the early stages, then slowed further until about 5-6 billion years after the Big Bang, and then began accelerating. What could cause the expansion rate to increase after such a long time? Not an explosion, not debris, not any explosive mechanism, only space itself expanding, with an internal form of energy that pushes space to stretch faster. This leads to an inescapable conclusion. The universe is not expanding because of an initial explosive impulse. The universe is expanding because space has energy that causes it to expand on its own. To understand this more clearly, go back to Einstein's field equations. In 1917, Einstein added a term to his equations, the cosmological constant lambda, to produce a static universe. Later, he called it the biggest blunder of my life. But in 1998, lambda returned as the lead actor. It is dark energy. Lambda is a form of negative pressure, a vacuum energy that causes space to expand faster over time. The more space there is, the more dark energy there is. And the more dark energy there is, the faster the expansion becomes. An explosion has no mechanism to do this. If the Big Bang were an explosion, you would expect the expansion rate to decrease over time. The data show the exact opposite. Type Ia supernovae are not the only evidence. BAO surveys, such as SDSS, BOSS, DSE, also show that distances between cosmic structures are growing faster than predicted by models without dark energy. Even the CMB from Planck shows that the universe is flat to a degree that only dark energy can balance the energy density to achieve the measured flatness. And when you combine all the data, CMB, BAO supernovae, large-scale structure, you find that the best model describing the universe is lambda CDM, a universe containing 68% dark energy, 27% dark matter, and 5% ordinary matter. Explosion has no place in this model. Explosion cannot explain 68% of the universe's energy. Explosion cannot explain why space accelerates. Explosion cannot produce a mechanism that makes every point in space recede from every other point faster over time. A bomb explosion does not produce a positive second derivative of the expansion rate. It only produces a negative one. Dark energy also gives us a new picture. The universe is not shot outward, but is pushing its own boundaries outward. No debris, no explosion center, no preferred direction. Only uniform expansion of space, growing ever faster, as though the fabric of the universe is being freed from all constraints and expanding without limit. This is not the physics of explosion. This is the physics of dynamic space-time, and it makes the idea of Big Bang as explosion look even more absurd than before. Imagine trying to describe the universe with the image of a bomb exploding. At the initial moment, the explosion would be extremely powerful, but then the debris would spread out and slow down. After a long time, the speed of the fragments would approach zero. Never, I repeat, never, do the fragments of an explosion speed up again billions of years later. But the universe does exactly that, and that is why dark energy is the strongest signature that we are not living in a post-explosion universe. We are living in a self-expanding universe, driven by the energy of space itself. It did not explode. It did not hurl matter into a vacuum. It creates new space. It expands itself. It pushes its own boundaries. But dark energy is only evidence that the universe today is expanding in a way that would embarrass any explosion. If you want to see evidence that the universe, right from its earliest moments, did something completely beyond the capability of any explosive mechanism, you must look at what Alan Guth in 1980 at MIT called inflation, the super expansion phase that lasted only an unimaginably brief moment, but determined the entire shape of the universe up to the present day. And this is what makes every explosion model not just wrong, but mathematically useless. The first problem inflation solves is the flatness problem. The problem of the universe's flatness. When Planck measured spatial curvature, full they all 0.00.0007, people realized something terrifying. The universe is flat to a degree indistinguishable from a sheet of paper on scales of tens of billions of light years. But without inflation, such flatness would require initial conditions tuned with precision, like throwing an arrow from Earth and having it hit a single atom on the moon. An explosion cannot do this. The debris of an explosion cannot distribute so perfectly as to create Euclidean space on cosmic scales. Only a process that stretches out all curvature, like inflating a balloon, can produce the extreme flatness we observe. That is inflation. The second problem is the horizon problem. Why does every point on the sky, even those separated by 46 billion light years, have the same CMB temperature within an error of only 0.00003 K? If the Big Bang were just an explosion, those points were never close enough to exchange information or heat. There is no way for them to equalize temperature before light and information could no longer propagate. Explosion, each region expands separately, non-uniform, but inflation explains it perfectly. Every point on the sky was once inside the same tiny region, had time to exchange energy, reach thermal equilibrium, and then was stretched by inflation to become the entire observable universe. It is like printing a small pattern on a balloon, then inflating the balloon to the size of a football field. The details in the pattern still retain their internal relationships, even though they are now very far apart. An explosion cannot do that. You cannot explode a balloon and still preserve perfect correlation between points on its surface. Inflating space can. The third problem is the monopole problem, an extremely vexing issue in particle physics. Grand unified theories predict the existence of magnetic monopoles, extremely heavy particles that should flood the universe, but we do not observe them. An explosion cannot explain why they disappeared. An explosion only disperses matter. It cannot uniformly dilute one type of particle on cosmic scales. Inflation explains it in one sentence. Monopoles exist, but inflation stretched space so rapidly that their concentration was diluted to near zero, like a drop of ink in the ocean. They did not disappear. They simply became undetectable. Now let us be direct. No explosion solves flatness, horizon, or monopoles. An explosion solves none of them, not one. It has no mathematics to do so. It has no physical mechanism to do so. No data supports it. Inflation solves all three problems with the same equation. And it is inflation that brings us to the most important feature: expansion faster than the speed of light. This is the point people often misunderstand. Inflation does not make matter move faster than light. It makes space expand faster than light. And Einstein allows this. Light is not overtaken. Points in space are simply pulled apart so rapidly that light cannot catch up, causing them to lose causal contact. In an unimaginably short time, from 10·4 tals to 10·4 tal seconds after the Big Bang, the size of the universe increased by a factor of 10·4 tals, equivalent to a proton, suddenly becoming the size of an apple. No bomb in any universe can do that. An explosion has an expansion velocity limited by the speed of force propagation through the medium. It cannot exceed light speed. Inflation is not limited. It has no velocity of energy propagation. It is a geometric process. Space multiplies itself, and that is something an explosion can never touch. Explosion has a center. Inflation has no center. Explosion produces non-uniform debris. Inflation produces uniformity. Explosion produces asymmetric distribution. Inflation flattens space. Explosion produces shock waves. Inflation leaves Gaussian fluctuations. This is not philosophy. This is data. Data from Kobe WMAPN. Planck all support inflation. From the shape of the power spectrum, nearly scale invariant, to Gaussianity, to the positions of the acoustic peaks. An explosion does not predict any of these things. It does not even know where to start to make a prediction. The subtle traces that Planck measured in 2013, small Gaussian deviations at 0.001%, comma baryon, dark matter density ratios matching perfectly, spectral tilt, n-tha 0.965, all fit inflation exactly. If the Big Bang were an explosion, you would have to explain, why is the universe flat? Why is the CMB uniform? Why do regions 46 billion light years apart have the same temperature? Why are there no monopoles? Why do density fluctuations have a nearly scale invariant form? Why does space seem to remember a very specific oscillation rhythm from the earliest times? An explosion answers none of these. Inflation answers all of them. And more, inflation predicts something an explosion does not even have a concept for. Primordial gravitational waves, ripples in space-time, generated by the ultra-rapid expansion. They leave traces in the B-mode polarization of the CMB. An explosion does not produce B-modes. An explosion does not curve space-time in that way. Inflation does. Even though the 2014 BICEP 2 experiment was mistaken due to galactic dust, the search continues. But inflation's prediction still stands. And that is what matters. Inflation does not just explain, it predicts, and its predictions match the data to an astonishing degree. All of this leads to an inescapable conclusion. Inflation is what removed the Big Bang from the image of an explosion. An explosion is the propagation of energy through space. Inflation is the self-multiplication of space itself. An explosion has limited velocity. Inflation has superluminal speed. An explosion creates chaos. Inflation creates order. An explosion hurls matter away. Inflation flattens the universe. But if inflation is the machine that stretched space to an incomprehensible degree, the next question is what created the initial ripples. The tiny density contrasts of Hentefeuerted later became galaxies, galaxy clusters, the cosmic web. This is where quantum physics enters the story, and it does something no explosion in any imagination could ever do: create structure from nothingness. In the quantum world, the vacuum is not empty. It boils madly with particle-antiparticle pairs that appear and disappear in ultra-short times. These tiny fluctuations are called vacuum fluctuations. Normally they operate on scales too small to have any cosmic impact. But inflation did the unimaginable. It stretched these minuscule quantum fluctuations up to galaxy-sized scales. In the brief interval from Hentefeuerted to Hentefeuerted seconds, space expanded so rapidly that the tiny fluctuations, which originally existed only on the Planck scale, were frozen, pulled out of their initial quantum state, and turned into classical density fluctuations across the universe. These fluctuations are the seeds of all later structure. No explosion can do this, because an explosion is a macroscopic process with no ability to turn quantum noise into uniform macroscopic signals across all of space. But inflation does this naturally, and the wonder does not stop there. When people analyzed the CMB data from Planck in 2013 and 2018, they discovered that these fluctuations follow a very special form called a nearly scale invariant spectrum. That means the amplitude of the fluctuations is almost the same at every scale, with only a slight tilt given by the index, therefore 0.965. This is the characteristic signature of quantum fluctuations being stretched during inflation. An explosion does not produce scale invariance. An explosion produces complex distributions that depend on explosion direction, material topography, density regions, shockwave speeds. There is no way an explosion can create a uniform spectrum across all scales like that. But inflation predicted exactly that spectrum back in the 1980s. 30 years before Planck measured it with 0.1% precision. This is not coincidence. This is the chemical fingerprint of quantum mechanics. When space expands ultra-rapidly, it magnifies the tiny fluctuations in the quantum field to macroscopic sizes. When inflation ends, those fluctuations become density fluctuations, slightly denser regions, slightly rarer regions. The denser regions are where gravity wins and eventually becomes galaxies. The rarer regions become voids. These are the seeds of the cosmic web. Stars, galaxies, galaxy clusters, and everything you see in the night sky. A bomb does not produce a nearly Gaussian distribution. Vacuum fluctuations do. An explosion does not produce scale invariance. Vacuum fluctuations do. An explosion produces chaos with no preferred modes. Vacuum fluctuations produce the power spectrum that Planck measured peak by peak. And most importantly, an explosion has no physical mechanism to turn quantum fluctuations into classical fluctuations. But inflation does, and that is the absolute distinguishing line between the two models. When scientists map the 3D galaxy distribution from surveys such as SDSS, BOSS, and DISI, they find that the power spectrum on large cosmic scales matches inflation's predictions almost perfectly. This includes the BAO, the peak positions, the tilt and thaw, the Gaussianity of the distribution. All of it reflects the trace of ancient quantum fluctuations stretched out. These fluctuations are not just echoes. They are the source code of the universe. And that source code contains not a single line resembling an explosion. Imagine tapping lightly on a cup of water. The ripples you create will disappear very quickly and never return in an ordered pattern. But if you freeze the cup of water at just the right moment, you preserve the ripple pattern. Inflation does the same. It freezes quantum fluctuations at precisely the right instant, so they become the foundational structure of the entire universe. From there, they grow into filaments, voids, galaxy clusters that we observe through telescopes. An explosion has no ability to choose the right moment to freeze chaos. Inflation chooses the exact moment down to 100 seconds. This is not fine-tuning. This is the natural dynamics of the inflaton field, causing the universe to inflate at superluminal speed and then shut off when the energy undergoes a phase transition. And when that process ends, the entire universe is seeded with tiny quantum ripples. No chaotic debris from an explosion can lead to this. No shock wave from a blast can produce a Planckian power spectrum. No Big Bang can create Gaussian fluctuations with n-thaw 0.965. But vacuum fluctuations can. And this brings us to a conclusion so strong it needs no embellishment. The origin of every structure in the universe, every galaxy, every star, every atom, is not the fragments of an explosion, but the quantum whisper of the vacuum, stretched by inflation into cosmic ripples. The universe did not explode into structure. The universe expanded from the quantum, inflated from the smallest ripples of nature. No explosion can do that. Only inflation plus quantum mechanics can sow the perfect seeds we see today. If those quantum ripples in matter density are the first traces of inflation, then there is an even deeper, more ancient, and more original signature that the standard cosmological model predicts: primordial gravitational waves, tensor perturbations in space-time itself. This is one of the boldest predictions of inflation, and also something that no explosion model in any imagined universe could ever produce. Because an explosion is the motion of matter through space. It cannot make space itself curve, stretch, and oscillate, but inflation does so naturally and inevitably. When the inflaton field dominated the energy of the universe during the period from 10 hours a quart to seconds after the Big Bang, it did not merely stretch the quantum fluctuations of matter fields. It also stretched the quantum fluctuations of the geometry of space-time itself. In general relativity, space is not a static background. It is a dynamical field. So when the energy of the universe was entirely in the inflaton field, small tensor metric fluctuations, ripples in the fabric of space-time, were also blown up to cosmic scales. And those are primordial gravitational waves. These are not the gravitational waves that LIGO detected in 2015 from black hole mergers. Those are late gravitational waves born from high-energy astrophysical systems. Primordial gravitational waves are something completely different. They are the direct echo of inflation, existing before there were even baryons, photons, or atoms. No explosion can produce waves of this kind. An explosion generates shock waves, sound waves, turbulent plasma, but never tensor oscillations of space-time in a nearly scale-invariant Gaussian form. From a purely mathematical standpoint, an explosion has no equations describing tensor modes, but inflation predicts them clearly. If space inflates faster than light, every quantum fluctuation of the metric is also stretched and frozen in exactly the same way density fluctuations were. The big question is, where do we find their traces? Fortunately, the universe has preserved them in the cosmic microwave background, CMB, through an extremely subtle effect called B-mode polarization. When primordial gravitational waves passed through the hot plasma during recombination, they distorted the light field in very specific spiral polarization patterns. They do not produce simple linear polarization, but characteristic twisting patterns. No other physical mechanism, no supernova, no galaxy, no plasma motion can create this pattern across the entire sky. B-mode polarization is the fingerprint of primordial gravitational waves. In 2014, the BICEP 2 team at the South Pole announced they had detected a B-mode signal, sending shock waves through the world. But later analysis showed that most of that signal came from dust in the Milky Way. Science does not jump to conclusions, but the story did not end there. Experiments such as BICEP Keck, SPT Pole, ACT Pole, and the upcoming Lightbird mission by JAXA continue to hunt for this signal, and each improvement narrows the escape room for inflation. The growing network of data increasingly allows us to determine that if primordial gravitational waves exist, their amplitude must be small but non-zero, exactly as inflation predicts. The most remarkable thing is no explosive model predicts B-modes. An explosion has no tensor modes. An explosion does not produce twisting polarization. An explosion does not make space ring like a gigantic drum, but inflation does. And if one day B-mode polarization is definitively detected with a signal exceeding galactic dust levels, that search will become one of the greatest contributions of human science. Direct evidence that space once vibrated on quantum scales, that ripples in space-time itself were stretched to cosmic sizes, and that the Big Bang was not the propagation of matter through space, but the creation of space itself. This carries such profound meaning that it overturns intuition entirely. Matter did not explode outward. Instead, the very foundation of reality, the metric of space-time, vibrated, expanded, froze, and left a trace of its own oscillation in ancient light. If primordial gravitational waves are found, we will have proven that space-time once existed in a quantum state. Inflation truly happened. The Big Bang was not an explosion, and the universe was not created from debris, but from quantum field oscillations. If primordial gravitational waves are the silent echo from the dawn of space-time, then one of the greatest mysteries of the modern universe comes from a completely different place. The way we measure the expansion rate of the universe, the Hubble constant, AP. And what is striking is that this mystery does not revive the Big Bang as explosion model, as many mistakenly think. It does the opposite. It absolutely reinforces the concept of an expanding universe, while at the same time hinting that what we understand today may only be the surface layer of a much deeper theory. This mystery is called the Hubble tension. The Hubble tension arises from something that seems simple. We have two independent ways to measure the expansion rate of the universe, and they do not agree. The amusing part is that both methods are correct. Both have data that are accurate beyond doubt, yet they yield two different numbers. The first method, called early universe measurement, uses data from the cosmic microwave background, CMB, especially from the Planck satellite in 2018. When you take the CMB map, measure the acoustic peaks, and run the alpha-LCDM model, you obtain 8A 67.4 Km/s/MPC. This is the expansion rate inferred from the physics of the universe when it was only 380,000 years old. But the second method, called late universe measurement, measures the recession velocity of nearby galaxies directly using the cosmological distance ladder, Cepheid type or supernova independent distance indicators. The SH0ES team, led by Adam Ries, has measured 8A 73S74 Km/s/MPC. This difference is not small. It is not within the error bars. It is not due to poor measurement. The two results differ by 5.6 sigma, meaning the probability that the difference is due to random noise is almost zero. So what is happening? And more importantly, does this save the explosion model? The answer is absolutely not. Regardless of whether the number is 67 or 74, both indicate one single thing: the universe is expanding. There is no scenario in which both methods lead to characteristics of an explosion. An explosion would produce a completely different velocity field, debris with high velocity near the explosion center, decreasing outward. But both methods of measuring 8A, despite differing, show velocity proportional to distance linearly, exactly as in space expansion, not like an explosion. Therefore, the Hubble tension does not open the door to the image of Big Bang exploding like a bomb. It only opens the question, why do two methods of measuring expansion rate differ so much? To answer this question, cosmologists have proposed a host of possibilities. One of them is perhaps the LTZDM model. The standard model of cosmology is not yet complete. Perhaps dark energy evolves over time instead of remaining constant like lambda. Perhaps there exists a new form of radiation, dark radiation, or ultralight neutrinos. Perhaps inflation needs modification. Perhaps the inflaton field has lingering after effects. There may even be weak interactions between dark matter and dark energy. Some bolder theories even question the nature of gravity on cosmic scales. But all these possibilities share one thing. They belong to new physics, not to anything related to explosion. An explosion does not explain the Hubble tension. An explosion does not predict two different values. An explosion has no dynamical model compatible with both early universe physics and late universe observations. An explosion is wrong at every level. So what does the Hubble tension say? It says that the universe is trying to whisper something to us, that the beautiful equations we use to describe it may only be the rough version of a much deeper theory. Perhaps the universe is telling us that dark energy is not as static as we once thought. Perhaps inflation was not simply a super expansion phase, but left some lingering aftershock that affects the expansion rate today. Perhaps there are undiscovered particles contributing to a different metric expansion in different epochs. And it is even possible, very possible, that the universe wants us to realize that our inference methods still rely too heavily on intuition. But whatever that message is, it is certainly not go back to the explosion model. The Hubble tension does not rescue explosion. The Hubble tension does not suggest debris. The Hubble tension does not break the expansion model at all. It only says that we do not yet fully understand what is driving that expansion. And there, science does not see discomfort. Science sees opportunity. Opportunity to extend the model, to discover new physics, to understand the universe not just as it appears, but as it truly is. If the Hubble tension is the universe whispering that we have not yet reached its deepest layer of physics, then the next story, the story that emerges directly from the internal logic of inflation, takes us to an even bolder realm. The idea that our universe is not the only universe, not everything that exists, not the entire stage, but only one bubble among countless other bubbles, each bubble a universe, all embedded in a larger space called the multiverse. This is not science fiction. This is a natural consequence of inflation, if you allow mathematics to lead as far as it wants to go. In the simple inflation model, the inflaton field is uniform across the early universe and causes space to inflate at superluminal speed. But in eternal inflation, the inflaton field does not shut off completely everywhere at the same time. Instead, it shuts off locally. In regions where the inflaton falls to a lower energy state, inflation ends, hot plasma appears, matter forms, and a local Big Bang occurs. That region of space becomes a bubble universe, like our universe. But in the surrounding regions, the inflaton field still holds high energy and continues to inflate. The result is that the overall space keeps expanding furiously, spawning other regions where inflation ends, other bubbles, each a universe. And this process can continue indefinitely. No stopping point, no final boundary, no single universe. This is one of the strangest outcomes of inflation, yet one of the most logical if you read the equations. No additional assumptions needed, no exotic new physics required, just inflation as we currently understand it. And the multiverse emerges as a consequence. Now I ask, can an explosion create a multiverse? The answer is absolutely no. An explosion cannot produce multiple regions with different on-NAF states. It cannot create continuously expanding space outside the bubble. It cannot create island universes within a sea of inflaton. An explosion is a single, unique, one-time event, non-repeating. Inflation, if correct as in Andre Linde's model, is a self-sustaining, self-reinforcing process. An explosion does not create baby universes, but inflation can create countless ones. Some multiverse models go even further, suggesting that each bubble universe may have different physical constants: electron charge, fine structure constant alpha, baryon, photon ratio, even the number of extra dimensions. This may sound crazy. I agree. But crazy is not the criterion for rejecting an idea. The only thing that matters is it a consequence of the model, and does the model fit the data? Inflation fits the data. Every time we measure the CMB from Kobe to Planck, it points to inflation working as the model describes. Not explosion, not debris, not shock waves. If inflation is correct, the multiverse is not just a possibility. It is almost inevitable. I am not claiming the multiverse definitely exists. I am not saying we have direct evidence. I am not selling you a neat story just to make you sleep better. What I want to say is, when you follow the logic of the best model we have today, inflation leads you to a concept larger than the Big Bang, a super universe in which the Big Bang is merely a local event. This changes the way you think about the classic question, when did the universe begin? If the multiverse exists, the right question becomes, when did our universe begin? And how many other universes have begun before it, or will begin after it? Looking in this direction, the Big Bang is no longer the beginning of everything, but only the beginning of one region of space within a larger structure. Not an explosion, but a region where inflation shut off, like a raindrop freezing on a window pane, while other drops continue forming around it. I also do not want to hide this. The multiverse is a controversial idea. Some physicists dislike it because it is difficult to test directly. Some like it because it explains finely tuned constants. But what I want you to see is the multiverse can only emerge from an expanding universe. It cannot emerge from an exploding universe. An explosion only produces a finite expanding space that eventually decays. Inflation produces an ever-expanding space background that constantly spawns new regions, constantly pushing the boundaries of the universe farther out. And if this is true, it renders human intuition completely meaningless, because the universe is not something that explodes like fireworks, but something that blooms like infinite soap foam. You see, I am not saying the multiverse is certainly real. I am only opening the door so you can see, when we move beyond the explosion model, we are not just correcting a small error in our picture. We are replacing the entire map. Explosion closes every door. Inflation opens countless ones. And behind each door there may be a universe with its own laws. No one knows for sure, but that is precisely the beauty of science. What we do not yet know is always far greater than what we do know. And the universe or multiverse is perhaps inviting us to keep walking, going deeper into the possibility of the multiverse. You might think the story has reached the final frontier of human understanding, but the truth is that the universe still holds subtler secrets, vague but persistent hints, hidden right in the very data we believe to be the most perfect, the CMB map from the Planck satellite. And it is those tiny anomalies, those small deviations, that are whispering that perhaps the LPDM model is only the first crude version of a much larger theory. These anomalies do not break the model. They simply do not fit perfectly, like slightly off-key notes in an otherwise perfect symphony. That makes them impossible to ignore. One of the most famous anomalies is the cold spot, an unusually cold region in the CMB map, larger and deeper than expected. It appeared in WMAP data and was confirmed by Planck in 2013 and 2018. According to LFDM, the probability of such a cold region existing is only a few percent, even lower. Some people suggest the cold spot is just a random fluctuation. Others think it could be the trace of a gigantic supervoid. But there are also bolder physicists who propose that the cold spot might be the signature of a collision between bubble universes in the multiverse. I am not saying that is correct, but the mere existence of the anomaly makes the question legitimate. Another anomaly is the large, small asymmetry. One half of the sky appears to have larger fluctuation amplitudes than the other half. This should not happen in the standard model, because the universe must be isotropic on large scales. But Planck sees it. No explosion can explain this. Explosion has no meaning when talking about entropy distribution on cosmic scales. But that asymmetry suggests that the shape of space, the topology of the universe, may be more complex than we thought. Perhaps space is not infinite and flat, but has a torus-like form, or some exotic manifold that allows light to loop around in non-intuitive ways. If true, this could explain some of the low multipole anomalies in the CMB power spectrum, especially the dipole and quadrupole being lower than predicted. Next is the question of curvature, spatial curvature. Planck results are consistent with flat space, but some statistical analyses suggest curvature might be slightly negative. If true, this opens the possibility that the universe is not Euclidean, but slightly saddle-shaped. The data are not yet conclusive, but they remind us that the current model is not absolute. And every time we see a small deviation in the data, we are looking at an opportunity to uncover physics beyond the standard. One of the most intriguing anomalies is the apparent non-random alignment of low multipole modes, known as the axis of evil. They should not be aligned. They should not have that ratio, yet they appear persistently across multiple experiments. Some say it is just a statistical fluke. Others say it is evidence for exotic topology. Others, even bolder, suggest it may be a trace of pre-inflation physics, a phase of physics before inflation that we do not yet understand. And every time an anomaly challenges the standard model, one thing becomes clear. None of these anomalies support the explosion model. An explosion does not explain the cold spot. An explosion does not explain multipole alignment. An explosion does not explain curvature. An explosion has no mathematical language to speak about spatial topology. These anomalies do not suggest a return to the explosive model. They suggest a new level of physics beyond LFDM, yet still built on the expansion of space-time, not on the propagation of material debris. And this is the part I love most. The part where I, as the storyteller, must confess one of the most important but least accepted truths. The universe is far larger than our imagination. And these anomalies are not flaws. They are signs that the horizon of knowledge is still very far away. They make us wonder what exists beyond the last scattering surface. What happened before inflation? How many spatial dimensions are truly relevant? Is there some other form of energy besides dark energy? Is there some kind of matter that interacts even more weakly than neutrinos? Could the metric of the universe have a fractal structure on super large scales? Every anomaly in the Planck data is like a small piece of paper slipped under the door, revealing that behind it lies a room much larger than we ever thought. No explosion model ever takes you there. Looking at the anomalies in the Planck data, those small but persistent deviations, we begin to understand a lesson the universe seems to have been trying to teach us for a long time. Nature does not care about your intuition. It does not care about what you think makes sense. Does not care about the mental images shaped by weak gravity, slow speeds, and flat space. The human brain evolved to dodge tigers, find fruit, understand the motion of rocks and trees, not to grasp the expansion of space, the curvature of the metric, or quantum gravitational waves stretched during inflation. Intuition is a survival tool, not a cosmological tool. And when we try to use intuition to describe the Big Bang, we immediately fall into the biggest trap, picturing everything as an explosion. When we hear molten gold, we imagine glowing liquid metal. When we hear expansion, we imagine a balloon inflating. And when we hear Big Bang, we imagine a bomb exploding. But the universe has no obligation to resemble a bomb. Nature does what it wants, not what we expect. Let us look back at our journey. Hubble showed the universe is expanding everywhere, with no explosion center. Penzias and Wilson measured a CMB, so uniform no explosion could ever produce it. B gave us a perfect blackbody spectrum, something chaotic debris could never create. WMAP and Planck gave us textbook acoustic peaks, the trace of oscillating plasma in expanding space, not shock waves from an explosion. Inflation magnified quantum fluctuations into cosmic structure, completely impossible in a macroscopic explosion. Quantum fluctuations determine the shape of the cosmic web, not random flying fragments. Dark matter built the skeleton of the universe, not asymmetric debris. Dark energy caused acceleration, a behavior that never occurs in an explosion. Every piece of data says one thing: the universe did not explode. It evolved according to its own equations. So why are humans still obsessed with the explosion picture? The reason is simple: intuition. Intuition helps us survive, but it is also what deceives us. When we step outside the scale it evolved to serve. Intuition says every motion must have a center, but the universe has no center. Intuition says matter must explode into space, but space itself expands. Intuition says fragments must be distributed randomly, but the cosmic web has a soft fractal structure formed from quantum oscillations and gravity. Intuition says energy must decrease over time, but dark energy makes expansion accelerate. Intuition says light must spread evenly in an explosion, but the CMB is uniform to 99.99% and has an almost perfectly Planckian spectrum. That is why intuition cannot be the foundation of cosmology. It evolved to help you throw a spear at an antelope, not to explain the evolution of space-time. And when we look at the Big Bang as explosion model, we immediately see it is not physical truth. It is the product of limited intuition. Ancient people were not stupid. They simply described the universe in the language their brains were familiar with, the language of fire, of explosions, of pressure, of matter flying apart. But the nature does not operate according to those images. It operates according to equations, according to tensor metrics, according to oscillation modes, according to quantum states, according to curvature, according to vacuum energy density. It operates in ways far beyond every intuitive image humans have ever created. When we call the Big Bang an explosion, we are trying to cram an infinitely wide physical horizon into a frame of understanding that is only large enough to explain rocks and fire on Earth. Explosion is the story humans tell other humans, not the story the universe tells about itself. And most importantly, every piece of evidence we have collected over the past century points to one conclusion: the universe has no interest in the explosion description. It does not operate by explosive dynamics, carries no trace of explosion, leaves behind no signature belonging to explosive processes. The universe expands unlike a bomb exploding. It has no shock waves, no debris, no preferred direction, no explosion center, no large temperature gradients, no asymmetric distribution. Instead, it has isotropy, near zero curvature, BAO, quantum fluctuations, inflation, Gaussianity, acoustic peaks, dark matter halos, cosmic web, acceleration. Those are the traces of Einstein's equations, not the traces of TNT. It is not the universe that is strange. It is your intuition that is strange. The universe simply does what the equations require it to do. You are the one who wants it to explode. But nature does not care about your desires. It does not try to make itself reasonable according to human feelings. It is only faithful to itself. And when you set intuition aside and truly listen to the data, really listen, you will see that the Big Bang was not an explosion, has never been an explosion, and will never be an explosion. It is the expansion of space. It is the evolution of the metric. It is the amplification of the quantum. It is the ancient oscillation of plasma. It is the asymmetric in time but isotropic in space expansion. Not fireworks, not a bomb, not a bang, echoing in a black box. Only mathematics, only nature. And nature, as always, does not care about your intuition. It only cares about truth. When we have traveled the entire journey, from quantum ripples, smaller than grains of reality, to galaxies, stretching hundreds of thousands of light years, to the cosmic web, spread like the skeleton of the universe, to dark matter, dark energy, inflation, CMB, BAO, Planck, Hubble tension, we can return to the starting point and look straight at the seemingly simple question, was the Big Bang an explosion? And after 21 parts, the answer is not only clear, it is astonishingly beautiful. The Big Bang did not explode. It has never exploded. It will never explode. No explosion center, no fragments flying outward, no shock waves, no plasma bursting like fireworks. Instead, the universe is the expansion of space itself, a stretching in which the distance between every point increases, not because matter was thrown outward, but because the geometric foundation of reality is stretching itself. The Big Bang was not the bang of matter, but the whisper of the metric, the gentle vibration of quantum fields, the opening of space. And when you piece all the evidence together, a complete picture emerges. Hubble showed recession velocity, proportional to distance linearly. No explosion direction. CMB uniform to near perfection. No debris or temperature gradients of an explosion. Kobe, WMAP. Planck measured a perfect blackbody spectrum, something no explosion could produce. BAO revealed ancient sound waves in plasma, nothing like any shock wave in an explosion. Dark matter built the cosmic framework, not asymmetric fragments. The cosmic web has a soft fractal structure, not random scattered matter. Dark energy caused acceleration, a behavior completely opposite to every explosion. Inflation made space inflate faster than light, a process an explosion cannot describe. Quantum fluctuations sowed the seeds of every galaxy. Not random debris could arrange itself into a nearly scale-invariant pattern. Primordial gravitational waves can only be produced by inflation. Explosion has no mechanism to generate them. Hubble tension shows the universe is more complex than the standard model, but creates no opening for the explosion model to return. Planck anomalies suggest new physics, new topology, but suggest explosion at no level whatsoever. All of this leads to a gentle but decisive conclusion. The explosion idea exists only because our intuition is not subtle enough to understand the expansion of space. An explosion is a human image created to interpret what we are not familiar with. It is the product of evolution, of physical experience on Earth, of the habit of understanding the world through memorable pictures. But when enough data is collected, when instruments are precise enough, when mathematics is strong enough, the explosion picture collapses completely, revealing behind it a deeper, more beautiful, more wondrous picture. Our universe did not need to explode to form. It only needed to open. And the beauty here is the paradox. What makes the universe grand is not explosive energy, but the simplicity of the equations. Not violence, but subtle expansion. Not the chaos of debris, but the order of quantum oscillations. Not the roaring noise, but the absolute silence as space multiplies itself. Nature does not explain to us why it chose this way. Instead of another, it simply leaves traces. Traces in the CMB, traces in BAO, traces in the cosmic web, traces in the helium ratio, traces in light polarization, traces in the Planck data. All of them come together to tell a story that Bang could never tell correctly. And when we face this truth, it is not disappointment, but awe that makes us feel small before the vastness of nature. Because if we misunderstood the Big Bang, one of the most foundational events of the universe, then how many other things are we also misunderstanding? How many concepts are we still projecting intuition onto a reality that does not care about intuition? How many structures, how many laws, how many phenomena beyond our imagination, simply because we still look at the universe with eyes evolved to throw stones and hunt prey? If right from the beginning we misunderstood the Big Bang, how many other things in the universe is intuition deceiving us about? That is the question I want you to carry with you when you leave this conversation, not the answer, the question. Because it is precisely questions like these, questions that make us feel small, that make science most powerful. And when you look up at the night sky, remember the universe did not explode to exist. It opened. And that opening is the most wondrous thing nature has ever done. If you want to continue accompanying me on even bolder journeys through physics, please subscribe so you don't miss any discovery. See you again on the next voyage through the universe, where the questions are even larger than we are.